Hi, folks, and welcome to a video module on how to interpolate. This is going to particularly apply to your thermodynamics course. So let's get started. Okay, so this little graphic here on the title page sort of represents what we're going to be doing or what you're going to be doing, particularly in thermo class, for properties, evaluating properties that are tabulated in property tables in the back of the book. So you might say, why do I need to learn how to interpolate in the first place? Well, I've got sort of three answers for you. One is that this is a math skill that's widely used throughout engineering, both in practice and also in the upper level classes. So you're going to be using some type of interpolation for the next 2 years of your undergraduate experience. Also, this skill is especially needed for the determination of tabulated thermodynamic properties here in your course. And then the third part is, realistically speaking, you may not be able to pass thermodynamics class without having this skill. Now, you don't have to be a master at it, but you have to be able to linearly interpolate for properties simply in order to be able to pass this class, because so much of our work depends on properties that are tabulated in the back of the book. And that's illustrative of what we do in industry as well. Okay, I've got two examples for this video. And the first one, at first blush, it's going to be very easy. This is a simple linear interpolation, a little bit like a homework problem, in fact. And so here we go. We're looking for the internal energy, the specific internal energy, little u, for H2O, water or steam, for the pair pressure, 150 kPa, and temperature, 305 degrees C. And if you're watching some of these videos, you say, wait a minute, this looks an awful lot like example 1 from the property evaluation video. Well, it is very similar, but I've changed a number a little bit. So for completeness, let's start where we should start. We've got H2O, okay, and we need to first thing we have to do is determine the phase of our property pair. And so what we're going to do is start by drawing the vapor dome on your own page. Here's the vapor dome, and you remember the different phases, okay? The phases of H2O relative to the vapor dome. And also you're going to want to draw in one line of constant temperature, an isotherm. That's just getting started. This is going to enable you to determine the phase of this property pair, okay? We will go to the pressure table. Suggest you go and look at that property evaluation video. I've selected the pressure table because I find that easiest to use when I have pressure and temperature. So what I've done is here's the pressure table for saturated water, H2O. Our pressure is 150 kPa or 1.5 bars. I look up the boiling point or the saturation temperature, 111.4. I use that to label the PV diagram that I just drew. Here's that line of constant temperature. The boiling point of water at a pressure of 150 kPa is 111.4 degrees C. That's the saturation temperature. Okay. For our problem, we need to draw in another line of constant temperature above 111.4 because our temperature is 305. The constant temperature line will be above saturation temperature then. And then we're going to look to see, where do we fit? Where do we land on our PV diagram so we can figure out what phase we're in? Well, there it is. Okay. We are in the superheated region for H2O. We have superheated vapor steam. So, okay. And so then you say, okay, now I know what table to use. I need to go to the superheated vapor tables for H2O. There we go. There's our conclusion. We just said that. Phase of superheated vapor. All right, so what we're going to do is we're going to fish out the superheated water vapor table. Happily, we find a pressure, 1.5 bars. We've got it. And now we start looking down the temperature table, and we see a value for 280. Here's U, and a value for 320. Here's U. Uh-oh. We don't have 305 tabulated. So that's trouble. That means we're going to have to interpolate. Okay. Now, what do we know at least? At least, numerically, where is U going to be? It's going to be some number. You don't even have to know how to interpolate. Common Sense 101 says that our number is going to be somewhere between 2778 and 2840. That's Common Sense 101. Okay. Now we're going to do the math. Okay, so we need to interpolate between the tabulated values. And so here's my recommended step one. Set up an interpolation table on your own page. Take the time with your pencil and paper to write down what you see in the tables, in the STEAM tables. Write down 280, then write down 305. That's what U value you're looking for, leave some space, and then write down 320. And write down the two numbers you know, 2778, 2840, and then maybe question mark or something like that in there. That's the setup. A number of students don't like doing this, but I strongly recommend that you develop this habit. I had to. Okay, now we're going to do a little mathematics, but what I want to do is I want to see if you can figure out with your eyes how to do the math without being given a formula. Now, we're going to get to the formula, but at least I found that by sort of looking at the table, looking at what I wrote down, I could figure out how to do the math without having to memorize a formula. And so here's my idea. I want you to think about proportions related to this table. Let's look at a proportion on the temperatures that we know. Here's a proportion between our temperature and the lower value or top value in the table. And here's the distance from the next tabulated value to the first tabulated value. So think about Z over Z total as a proportion. Okay, so you got that in your mind. It's a proportion, isn't it? Okay. The next thing here is use Common Sense 101 to see U is going to be at least 2778.6. It's going to be at least that number. And it sure as hell not going to be bigger than that number, okay? So it's at least that number plus some proportion of this difference. It's going to be a proportion, Z over Z total, of the difference between 2840 minus 2778.6. Okay, does that, you got it? So it's my hope that you've got this in your head, in your eyes, guiding you rather than just blindly following a formula. Blindly following a formula can work, but I don't think you're doing yourself any favors by blindly following a formula that's in the book or in some help, tip sheets or things like that. They're valuable. You can use them, but I don't recommend it. All right. So now let's go and look at the math. Okay. I just repeated that. So we know that our value U question mark is going to be bigger than 2778 plus the proportion of this difference. So look at that with your, okay, so here we go. U is at least 2778 plus a proportion. Look at Z. Here's my my Z amount, 305 minus 280. Here's my Z total amount, 320 minus 280, times the difference between the tabulated value. And I've written those out, okay? Now, some students, myself included back in the day, very often I would have this table written down, but I wouldn't write down the first line, but I would write down the second line. U is 2778.6. With my eyes, I did the math. 305 minus 280 is 25, divided by 320 minus 280, that's 40. I'd write that down, times, and then I would write out this difference, 2840.6, because always these properties in thermo, they're always, they're never integers, right? It's not math you can do in your head. Okay, so there's our approach. Okay, and so if we plug and chug, we do the math here. and we get a number 2817.4. That's the linear interpolation. And let's check, does this numerical result make sense? So imagine how quickly you can do that. Just in your head, you're taking a quiz, you're doing a test. You can still do this quickly by looking with your eyes. Okay, that makes sense to me. 2817 is in between these two numbers. I'm going to blast ahead. If it's not, I'm going to go back and have to reinvest some time in doing my math correctly. Okay, there's the first example. Let's recap what we just talked about. So you can kind of scope out how to do the math. And so I've tried to show this. You're writing down this table on your sheet of paper. And what I've done is I've exchanged variables for the numbers in the example. So set up your table on your paper in the order that you see it in your thermo book. Don't be sorting different things. Just write it out the way you see it with your eyes. And therefore you don't even have to look up this formula in your book. You don't have to look up this formula in a tip sheet. You can write down the formula on your own. Y, this variable, equals Y1 plus a proportion. It's going to be X minus X low divided by the quantity X high minus X low times Y2 minus Y1. So there's the formula. There's the formula. So either way, so I've given you two ways to do it. You can write down a formula and blindly follow it. Okay, that can work. Also, I want you to get a vision in your head about what you're doing. Okay. Example 1 complete. Not too bad. Not too painful. A little painful, but doable. Okay, let's go to example 2. That is more complex, but still doable. Now, okay, and so here's our problem. Determine the specific internal energy U for H2O at a pressure of 175 kPa, it's a different pressure, and 305 degrees C. The exact same temperature that we used in example 1. We just changed the pressure a little bit. Okay, this is, in what's coming ahead is, you're going to have to do a double interpolation to find U. All right, now, don't panic. Okay, I got to tell you that I'll bet 90 to 95% of your work in thermodynamics class this semester is going to be, for example, 1 type situations, single linear interpolation. So do not panic. I would expect most instructors, most professors are coming up with homework assignments, quiz assignments, test assignments, probably that are sort of selected specially for you, so that you only have to interpolate for 1 single variable rather than 2. There will be a few problems where you have to double interpolate. So let's cover this. All right. So let's go towards the solution. We're sort of repeating. We don't need to go all the way back to our TS diagram, because we're going to go to our pressure table and look at what's tabulated in our pressure table. We're looking for 175. I don't see it here. I see 1.5 and 2. Okay. And so we're somewhere in between there. Let's visually look. How about the saturation temperatures? 114 and 120. Okay. We're at 305. And so again, common sense 101 says, almost by inspection, now that we're getting more experience, our phase is going to be superheated vapor for this problem. Okay, because we've got some previous experience now in doing this on paper. Okay, superheated vapor, right? We're looking for U. Let's go to the superheated tables. So we will. And so here's screenshot. Okay, now we'll go shopping for pressures in our superheated table. Here's 1.5 bars. That's not us. 3 bars. That's not us. Our pressure is 1.7. We're somewhere in between here, and nothing is tabulated in between. Darn it. Okay, now let's look at temperature. 280 is tabulated. 320 is tabulated, but 305 is not tabulated. Oh, no. 305 isn't tabulated either. So we're going to come up with something in between these two. Oh, boy. Oh, boy. what a mess. Now, looking ahead, remember the blind use of formulas. I got to tell you that a provided formula for this math, I've never even, I'm sure it exists, but it would be nearly impossible. There'd be so many variables involved. It would be impossible to blindly follow some formula for this. And so again, what I want you to do is get a feel for, if I were faced with this problem, what would I do? The answer is, we're going to double interpolate. I'm going to take you through the steps where you need to do it. First thing is, let's create us a table where we determine U at 305 for 1.5 bars. It's not what we're looking for. Let's just do it. Then let's create a table where interpolation where we determine U for 305 degrees C at 3 bars. Well, that's going to get us halfway there. Then we will take that result and do yet another interpolation to get our desired pressure. That's our approach. Make sense? I hope so. Okay, so we've planned our work. So here we go. Here is, I'm going to write down what I see in the book. 280, 305, that's space available for what we're trying to find. 320, it's in the book. So I write down the U values from 150 kPa. Then, off to the right on my sheet of paper, I write down the same table for 300 kPa. I keep these tables separate. Okay, temperatures are similar. Okay, leave space for your temperature, 305. Okay, and write down the 2775 and 2838 from the 300 kPa table. I put U equals question mark, U equals question mark. Okay, that's the setup. Now we'll do the math, right? So I'm not gonna add slides to do this math, but you see, let's just look at this one. This value is going to be at least 2775 plus a proportion of the difference between this number and this number, okay? And the proportion is going to be 305 minus 280 divided by 320 by 280. I can do that. I know the big part is 40. I'm having trouble doing the math on those two right now. Let's go to the next slide. Okay. Well, so I do the math, okay? And I find these two numbers, okay? So I've done 2 interpolations, haven't I? Okay, but I'm starting to fill in my work that I've written on my sheet. Okay, great. Well, now I have some values at both of them are at 305 degrees C. Check. But I still need to figure out the U at my pressure of 175. So I'm going to drop down on my paper and set up another little table. Here's my another little table, okay? The left-hand side is pressures, 150, 300, and in the middle, that's what I'm looking for, 175. I simply translate my numbers, 2817 at 150, 2810 at 300, okay? Put them down, and next I'm going to do a linear interpolation to this. Now, use your eyes to anticipate what number will you expect. Well, don't you expect a number in between these two, right? And so for this example, this is a very common situation in thermodynamics, I'm going to expect a numerical number that's less than 2817, because down here I got 2810. That's a key thing to look at with your eyes. This is why it pays off for you to write this stuff down on your pencil and paper, on your paper using your pencil. Okay, so now we're going to do the math. U is, well, it's at least this much. We're going to end up subtracting a number by a proportion. This little proportion, 175 minus 150, divided by 300 minus 150, that's my proportion, okay? That's going to be some fraction, times the difference, 2810 minus 2817. So look at that. That's going to be a negative number, isn't it? A negative number. And so we're going to have a proportion times a negative number. We're going to end up subtracting numerically from 2817. And I've got 2816.2 kilojoules per kilogram for U for that pressure of 175, temperature 305. Check. Does the numerical result make sense? It does to me. 2816 is a number between these two numbers. Got it. So at least it makes sense. Now, as you can imagine, I've graded a lot of thermo tests. Not quite so many quizzes, but I've graded a lot of thermo tests. And I got to tell you that I don't give students the credit for recognizing they've made a mistake, but it is wonderful. They get partial credit if they come up with a number that is wrong, but they circle it and say, this doesn't make sense, should be between 2817 and 2810. And I got to tell you, for me, in my world, that goes a long way in my perception of the way a student is performing on a test. So it's not a matter of, oh, that's -2 points, that's -3 points. I don't do it that way. If a student writes down some blunder value and continues blithely working along, that's not worth a whole lot of partial credit. But a student who recognizes a blunder, circles it, and explains it a little bit, man, that's very worthwhile to me. I got off track here a little bit. Okay, let's recap example 2. Double interpolation involves multi-steps of single linear interpolation. So it's much more time-consuming. Double interpolation is a time-consuming process. You will end up doing this on your homework problems. Typically, it's used in the superheated vapor phase. If you go back and look at the property evaluation demo that I did, you'll see that in the compressed liquid phase, we won't be doing double interpolation. So you're typically going to find this in the superheated vapor phase of either H2O, propane, refrigerant, ammonia, those type of phase change substances. You're going to perform 2 linear interpolations for the first independent variable, and then you're going to use the results of that work for a single linear interpolation for the second independent variable. Okay, so I declare you excellent, skilled interpolators. So key learnings that I hope you got from this video. Use interpolation when your independent variable value is between 2 tabulated values. That's when you use interpolation. Okay. You want to write down the setup in your own little table using your own pencil and paper. That is a key to success here. That's a key. And then remember the proportion setup. Once you've written down your little table, it's easy to see the proportion idea in your first variable and apply that proportion to the second variable, what you're trying to find. So that's it. And so I hope you're saying, man, this sounds kind of tough, but I'm going to try it, and I think I can master it. So I wish you all the best in mastering this. It takes practice, practice, practice. Okay, so keep up with your homework, and that's going to enable you to practice, practice, practice on this interpolation work.